Okay, someone's supposed to remind me if that's a recording. Is that someone here? Okay, so I'm now recording. I haven't done anything yet. I'm now going to screen share. Good. Okay, let's start from here. Okay, now recording and it's on the screen. We're good. Okay, so in the first class, I introduced systems of linear equations, right? So in 2 dimensions, you have a line that can be expressed as a linear equation of this form. In 3 dimensions, you can express a plane in this form. Okay, right? And so we had a definition of a linear equation, which was here. And we had the notations for linear equations in 2 and 3 variables can be simplified a little bit. Okay, a homogeneous linear equation is when it equals 0. Excuse me. Examples of linear equations, nonlinear equations. Okay, we had the notation for a general linear system of m equations in n unknowns. So this whole thing is notation for a general linear system of m equations and n unknowns. Okay, and then we had a notation as ordered n tuples for a solution of a linear system and n unknowns. So this was a whole lesson, and it can't really summarize it for you in a few seconds. You kind of have to read through every definition in order to summarize it. Okay, but these were all the definitions that we went over. Okay, so you need to make sure you know and understand those definitions. You may have to read that again and watch the video again. Okay, so in lesson 2, we're going to continue where we left off. And so the last thing we talked about was a solution of a linear system. Okay, those solutions could be expressed as ordered pairs or ordered triples, ordered n tuples they're called. And so when you think of an ordered pair, you normally think of a point in the xy plane, right? And so what this leads to, the fact that we can express the solutions of linear systems as ordered pairs or ordered 3 tuples, ordered n tuples in general, this leads to the idea that you can interpret solutions geometrically. Okay, so you have to make sure to have your mic. Somebody. I'm just gonna mute it. Okay, so you have to make sure to mute your mic so that doesn't happen. Okay. Okay, so generally, okay, a solution to a linear system of m equations with n unknowns can be with m unknowns of the form x1 equals s1, x2 equals to s2, x3 equals to s3, ... xn is equal to sn. Okay, so the solution is the assignment of each unknown to a specific number value in which that assignment makes every equation in your linear system true, right? So that was a solution, right? So a solution to a linear system of m equations with n unknowns of this form can be written as an ordered n tuple. That ordered tuple is S1, S2, S3, S sub n. Which is called an ordered n tuple. Okay, so this is an example of an ordered n tuple. With this notation, it is understood that all variables appear in the same order in each equation. If n equals 2, then the n tuple is called an ordered pair. If n equals 3, then it is called an ordered triple. Okay. Okay, so when you have a linear system which has exactly 2 unknowns, a solution would have to be assigning a value to each of those 2 unknowns so that every equation is true. Okay, the solution is that assignment, meaning the assignment is, well, what is x1 equal to? What is x2 equal to? What are the values of each of them that make every equation true? That assignment is a solution of that linear system. Okay, and you express a solution as an ordered n tuple where the components of the ordered n tuple correspond to the assigned values of your unknowns in your linear system that satisfy every equation in that linear system. So when you have 2 unknowns in a linear system, a solution is an assignment that gives 2 values, one for each of the 2 unknowns. An ordered pair like 1, 2 would say you assign the first variable the value 1 and the second variable the value 2. And if you do that as a solution, that what it's saying, being a solution means that that assignment will make every equation in your linear system true. Okay, right? If you assign the wrong values to your unknowns, then you could have an equation where after you plug in those values, the 2 sides are not equal, right? If you have x1 plus x2 equals 5, and you assign x1 the value of 100 and x2 the value of 0, then that is not a solution to that one equation, right? Okay, and if you have a linear system with 10 equations, then you have to put the same values for all 10 equations. And if all 10 are true, then that assignment is a solution, and you express that solution as an ordered n tuple. The ordered n tuple is just a short way of telling the reader what values you're assigning to each unknown to make every equation in your linear system true. Okay. Okay. So that is, we just talked about a solution of a linear system and notation for a solution of a linear system. Next is linear systems in 2 and 3 unknowns. Okay, so linear systems in 2 unknowns arise in connection with intersections of lines. Okay, so one linear equation with 2 unknowns would be expressed as a line. Another linear equation with 2 unknowns would be expressed as another line. Points on the line correspond to solutions of that single equation, right? Points on the line correspond with solutions. Points not on the line correspond with things that are not solutions. Okay, so if a line represents all the solutions of one linear equation, another line represents all the solutions of another linear equation, then those 2 lines may intersect. If they intersect, the point of intersection would be a point which represents a solution to both linear equations. Make sense? Okay, so you could either have 2 lines that intersect or 2 lines that don't, right? If 2 lines don't intersect, they're parallel, right? Well, actually, sorry, you have 2 intersecting lines, right? Now, if 2 lines don't intersect, let me put another way. You have lines that look like this, where they intersect at a single point. You have lines like this, which you call parallel, which never intersect, so they intersect at 0 points. You have 2 lines that are exactly the same line, and they intersect at infinitely many points. Okay, so that means when you have 2 lines, either they intersect at 1 place, at infinitely many places, or at 0 places. Okay. All right. Anyway, I'm kind of rushing ahead. I'm kind of going ahead of myself here. So for example, consider the linear system A1 x plus B1 y equals C1. And the second equation in that same linear system is A2x plus B2y is equal to C2. Okay? In which the graphs of the equations, in which the graphs of each equation is a line in the xy plane. So each of those equations is each graphed by a line in the xy plane. So this is what I was saying out before. Each solution x comma y of this system corresponds to a point of intersection of the lines. So there are three possibilities. One, lines may be parallel and distinct, in which case there is no intersection, and consequently no solution on the linear system. Okay.
Professor,
Yeah.
are we gonna get like examples about it?
Yeah. Well, yeah. So what I want to do with the examples is kind of just draw a general picture, because there'll be lots of examples. So yeah, let me just keep going, and I think this will make more sense for what I'm going to do soon. Okay. So if you have this linear system, right? With these two linear equations, right? Each of these equations is graphed by a line, right? Okay, points on the line correspond with points that represent solutions to that linear equation, okay? And the other line, the points on the line correspond with the solutions to the other linear equation. Points not on a line correspond with assignments of values to the unknowns that do not satisfy the equation, that do not make the equation true, okay? And so if the solutions of each linear equation is represented by a line, well, if you have two lines in the xy plane, what are the relations? Well, the possible relationships of two lines in the xy plane? Okay, well, in one, the first thing here, the lines may be parallel and distinct. Being distinct means they're not the same, right? So if you have two lines that are parallel, they have the same slope and they're distinct, then that means they never intersect. And so consequently, that these two lines, since they never intersect, the solutions of these two linear equations, they don't have any solutions in common. So there's no way to have a solution to both equations in your linear system, because there is no point that is on both lines at the same time. That makes sense? So possibility one is that these lines are parallel and distinct, which means your linear system has no solutions. The second possibility is that the lines may intersect at only one point, in which case the system has exactly one solution, right? So if case one doesn't happen, if they're not parallel and distinct, right? Parallel and distinct, another possibility, which is separate from that, is that they intersect, okay? So if they intersect, they're definitely not distinct and they're not parallel. Okay, so this lies outside of possibility one. So they may also intersect. Now, if they intersect and they intersect at one point, so that's another possibility. So if they intersect at exactly one point, and that means you have exactly one solution to your linear system. This is exactly that one point represents exactly one assignment of values to the unknowns in your linear system that make both the two equations true. Three, the lines may coincide, meaning the two lines are the exact same line. Okay. In which case, there are infinitely many points of intersection. All the infinitely many points on the common line. And consequently, the linear system has, and consequently, the corresponding linear system has infinitely many solutions. Okay, so if you have if you have a linear equation represented by this line, and you have another linear equation represented by the same line, then all of their solutions coincide and there's infinitely many of them. And so the solutions of the linear system of those two equations represented by the same line, common line, there's infinitely many solutions. Okay, and those are the only three relationships that these two lines can have: parallel and distinct, intersecting at one point, the same line intersecting at infinitely many points. Okay, so these are the only three possibilities, meaning that your linear system, this linear system, there can only be 0 solutions, exactly 1 solution, or infinitely many solutions. There cannot be 2 solutions. There cannot be 5. There cannot be 100. There cannot be 1,000,000. There cannot be 3. There can only be exactly 0 solutions, exactly 1 solution, or infinitely many solutions. Can't be half a solution. Okay, so those are the three possibilities because we see that geometrically by the relationships of the lines, 2 lines in the XY plane. Okay, as far as the examples, so for case 1, right, if they're parallel and distinct your lines, for instance, if you have the line x1 plus x2 is equal to 0, and you have another one, x1 minus x2 is equal to 0, then wait, there's no intersection. Sorry, wait, that's not. Let's say 2x1 plus 2x2. No. Let's do that first. x1 minus x2 equals 0. And so then another equation could be x1 minus x2 is equal to 1. Okay, so this linear system is represented by 2 lines which are parallel and distinct. Okay, so if you drew this line, okay, so let me go to the whiteboard. So the linear system I just wrote down was x1 minus x2 is equal to 0, and x1 minus x2 is equal to 1. But I just want to use colors for a second. So x1 minus x2 is equal to 0. And then the other one is going to be x1 minus x2 is equal to 1. So if you represent each of these equations by lines in the xy plane, then x1 minus x2 is equal to 0. We're using x1 and x2. So here's x1 and here's x2. Okay, so x1 minus x2 equals 0. That's equivalent to the equation, has the same solutions as the equation x1 equals x2. And so x1 equals x2 is like y equals x. It was just going to go across like that. It's going through the origin. Okay, it's going through the origin there. Okay, so this is the line x1 minus x2 is equal to 0. The other line is x1 minus x2 is equal to 1. That's the same as the line x1 is equal to x2 plus 1. Or that's the same as x2 is equal to x1 minus 1. So this is the same as the line. This is also represented by the line x2 is equal to x1 minus 1. And so this is like y equals x minus 1. this is like a translation of y equals x, but down 1 unit because it's a -1 here. So then using pre-calculus, you have this line. This is a line. And this is x1 minus x2 is equal to 1. Okay? And so you see they're parallel and they're distinct. And so they have 0 intersection points. The slope of each line is 1, but they're different lines. It's the red line is the blue line shifted down by 1 unit. And so that means that this linear system, a linear system is an entire finite set of equations. So in the box, this green box is one linear system. That linear system has 0 solutions because there are 0 intersection points of those two lines. Okay? Okay, so this linear system is represented graphically in this way, and the geometric interpretation of this linear system is illustrating that there must be 0 solutions of it. Okay, and so that's
Professor?
case 1.
Sorry, I'm a bit confused. Like, where did like the 0, since they're the same equation, why is it like 0 and then 1 and the other one is equal to 1? I think
I'm writing 2 equations of a linear system. So one of them is x1 minus x2 equals 0. The other one is x1 minus 2 equals 1. And so by changing a 0 to a 1 here, it ends up being that I'm shifting this line geometrically down by 1 unit. Wait, so what's your question? What's your question?
Oh, no, I was a bit confused about the difference with equaling it to 0 and 1, but then I get it because it's like a parallel.
Well, so see how x1 minus x2 equals 0, right?
Yeah.
You agree with me how that's x1 equals x2?
I guess. Yeah.
Right, add x2 to both sides. What do you get?
Oh yeah, 0, right?
You get x1 equals x2, right?
Okay. Okay.
Do you know what I'm saying, or no? Or are you confused? Do you know what I'm saying?
No, I'm trying to. Yeah, I'm slowly getting it.
Right. If x, so I'm not asking you to get the whole thing. I'm just saying this. If you x1 minus x2 equals 0, add x2 to both sides, right? When you add the same amount to both sides of an equation, the solutions are the same. So x1 minus x2 equals 0. When you add x2 to both sides, x1 equals x2. So this equation, x1 equals x2, has the same solutions as x1 minus x2 equals 0. Does that make sense?
Oh, okay, that makes so much sense.
Okay, well, do you remember the line from pre-calculus y equals x?
Yeah.
Right? You would graph it like this, right?
Yes, definitely.
Right, so instead of y equals x, it's x1 equals x2. So you see how the blue line is representing that equation, x1 minus x2 equals 0?
Oh, so it's like a imaginary y in a way.
No. It's a line, right?
Yeah. Okay, I think
It's
I
just a line,
understand.
right?
Yeah.
So you see how this blue line graphically represents the line x1 equals x2?
Yes.
Okay, now you have x1 minus x2 equals 1. Do you agree with me that algebraically that's the same as x2 equals x1 minus 1?
Yeah.
I add x2 to both sides, right?
Yeah.
We have x1 equals 1 plus x2, and then subtract 1 on both sides, x1 minus 1 equals x2.
Yeah.
Are you lost, or do you
No, I'm understanding.
Okay, good. Okay, so x2 equals x1 minus 1 is the same as this. Okay, now how do you draw the line x2 equals x1 minus 1? It's the line x2 equals x1, and then you just shift it down by 1 unit because that's by transfer. In pre-calculus, you had transformations of graphs. So when you do a minus 1 here, you're just shifting the line x1 equals x2 down by 1 unit. So you get the red line here. Does that make sense?
Yeah, thank you so much, Professor.
Okay, you're welcome. If you have the line y equals x, right, you graph it a normal way. If you have the line y equals x minus 1, that's a shift down by 1 unit of the other graph. Okay, good. Okay, and okay, good. Okay, so you have those two lines graphically representing this linear system, and zero intersection points correspond with zero solution. That's case one. Case two, the lines may intersect at only one point, in which case the system is exactly one solution. So intersecting at exactly one point. So if you have a linear system like this, if you have x1 minus x2 is equal to 0, and then you have another one, x1 plus x2 equals 0. So I'm going to use different color again. So you have x1 plus x2 equals 0. Okay, so now let's talk about the graphical representation of that linear system. So then you have the x1 axis and you have the x2 axis. And so x1 minus x2 equals 0, that corresponds with the same line as before. This line, which goes through the origin. So that's the blue line representing that first equation. The second equation, well, x1 plus x2 equals 0 is equivalent to the equation x1 x2 is equal to negative x1. That's a 2. Okay, so x2 is equal to negative x1. Well, that's the same as like y equals negative x. And so then what you get is the other diagonal line that crosses the origin also, but perpendicularly in this way, right? So now you have this linear system, this one linear system consisting of those two linear equations. And since you have these lines and they intersect at exactly one point, that means this linear system has one solution, exactly one solution. That one intersection point of those two lines right here, the origin, right? So if you plug in x1 equals 0 and x2 equals 0 into this equation, you get 0 minus 0 equals 0. And if you plug into this one, 0 plus 0 equals 0. And so that's the solution. Also, if you plug anything else other than 0 and 0, it doesn't work for both. So if I plugged in 1 comma 0, x1 equals 1, x2 equals 0, you get 1 minus 0 is not 0. 1 plus 0 is not 0, right? So then this would fail. So any point other than this point is not on the intersection of these two lines and corresponds with an assignment which does not satisfy every equation of this linear system. So this linear system has exactly one solution. This is the example of case 2. Okay, and then the third case was the lines may coincide, they have the exact same line. Okay, so you have two lines, a linear system where the two lines are the exact same line. Okay, so let's say you have the equation x1 minus x2 is equal to 0. That's your first equation. And let's say your second equation is 2x1 minus 2x2 is equal to 0. I'm going to use red. So then you have 2x1 minus 2x2 is equal to 0. Okay, so now we're going to graph each of those lines and see the relationship between those two lines to find out how many solutions this linear system has. So you have the x1 axis and the x2 axis. So if you have x1 minus x2 equals 0, that corresponds with the equation x1 equals x2, and that corresponds with this diagonal line, which I'm going to draw again. Okay, this goes through the origin. Okay. So now if you have 2x1 minus 2x2 equals 0, and you draw the line representing it, you will get the same exact line. This is the exact same line. It's not perfect, but you see, right? So these two linear equations, their solutions form the exact same line. Okay, and so this actually has infinitely many solutions. Okay, and this is an example of case 3. Okay, so I was asked to give examples of each, so I just did, right? So does that help? Okay, so these are examples for each of the 3 cases in this thing here. Okay. So the examples are, how about this on whiteboard? Examples on whiteboard of each of the 3 cases. Okay. So in general, we say that a linear system is consistent if it has at least one solution, and is inconsistent if it has no solutions. Okay, so thus, a consistent linear system of 2 equations in 2 unknowns has either one solution or infinitely many solutions. There are no other possibilities. Okay. The same is true for a linear system of 3 equations and 3 unknowns. Okay, so in general, we say that a linear system is consistent if it has at least one solution, and is inconsistent if it has no solutions. So a consistent linear system has at least one solution. There are only, again, 3 possibilities: 0 solutions, exactly one solution, or infinitely many. And so since a consistent linear system has at least one solution, that means that there are now only 2 possibilities for a consistent linear system: exactly one solution or infinitely many solutions. Okay, and it doesn't matter how many equations or how many unknowns you have. If it is a consistent linear system, it can only have exactly one solution or infinitely many solutions. Okay, so the same is true for a linear system of 3 equations and 3 unknowns. And so you could represent such a system as A1x plus B1y plus C1z is equal to D1. That's the first equation in that linear system. The second equation would be A2x plus B2y plus C2z is equal to D2. When you're doing linear systems with 2 and 3 unknowns, the notation is sometimes simpler in a sense that you're using less letters or something, but it's not less letters, but you're using those indices. It's actually a little more confusing. I prefer the general one where you have to understand the notation language. So if you have if you learn a system with 3 equations and 3 unknowns, your unknowns are x, y, and z, and right, you have your coefficients, right, where the a's are the coefficients of x, the b's are coefficients of y, and the c's are coefficients of z, and d's are the constants at the end of the equation. And here the subscripts are telling you which equation you lie in. So A1 is a coefficient of x in the first equation. A2 is a coefficient of x in the second equation. A3 is a coefficient of x in the third equation. B1 is the coefficient of y in the first. B2 is the coefficient of y in the second. B3 is the coefficient of y in the third. C1 is the coefficient of z in the first. C2 is the coefficient of z in the second. C3 is the coefficient of z in the third. D1 is the constant at the end of the first equation. D2 is the constant at the end of the second equation. And D3 is the constant at the end of the third equation. Okay. Okay, so if you have a linear system of this form in which the graphs of the equations are planes.
Professor, what's D1, D2, and D3? You said constant?
Yeah, they're all constants. So if you had a linear system like 2x plus 3y plus 4d is equal to 7, d1 would be 7. And then if the next equation was 3x plus 5y minus 9z is equal to 0, d2 would be 0. And then if your next equation was 3x plus 3y plus 1 plus 11z is equal to 4, d3 would be 4.
Okay, got it, Professor. Thank you.
Okay, you're welcome. Okay, I'm going to delete that. Okay. It's on the video. Okay. Okay, so then in which the graphs of the equations are planes. Okay. Okay, so then each of these linear equations are representing planes in 3 space. That was mentioned in the first lesson. So the solutions of the system, of such a system, if any, correspond to points where all 3 planes intersect. So again, we see that there are only 3 possibilities. 1, no solutions. 2, exactly 1 solution. And 3, infinitely many solutions. Okay, so when you draw 3 planes in 3 space, and you look at all the points with that lie in all 3 of those planes, you only end up with these 3 possibilities for how many points are in that intersection. Either there's 0 points of intersection, exactly 1 point of intersection, or infinitely many points in the intersection. Okay. So what I'm going to do now, and this takes a little effort. Okay, so what we're going to see is see the whiteboard for an illustration of this. Okay, so now I'm going to illustrate this idea that when you have 3 planes in 3 space, how many points could there be in the intersection of those 3 planes? It's either 0, 1, or infinite. Exactly 0, exactly 1, or exactly infinitely many. So I'm going to draw each of them. So there's this possibility where you have a plane. You have another plane that's parallel to it. So that's not intersecting, it's just below it. Like if you have 2 sheets of paper, I have to see my screen for a second. Let me see. We're on the whiteboard, good. But if you had 2 sheets of paper that were parallel, right, that never intersected, and these were planes that went out to infinity, each of them, there would be 0 intersection points, right? So that's what I'm drawing there. And then there's 3 equations, right? And 3 unknowns. And so each of those 3 equations is a plane. And so I'm going to do this again. And what I'm saying here is there's 3 planes, one on top of the other, and they don't intersect. Does that make sense? So that's what I'm drawing here. And so sometimes you'll also draw lines going out, and those lines will just it's just kind of illustrating, those lines are illustrating the idea that these are not rectangles, these are lines that are going out in all directions, okay? But because I'm going to be drawing so many of these, I'm not going to be drawing the arrows in this example, but I want you to keep in mind that that's what's happening here, right? In none of these pictures I'm drawing are these just rectangles, they're all going out in all 4 directions. Make sense? Okay, so for all the future pictures, I'm not going to be drawing these for this example right now. I'm not going to be drawing these arrows because it'll be easier to see without the arrows. Just for this first one. Okay, so you see that That's what's happening now. Okay. This one's also going out in that direction. Okay, so this is one example of 3 linear equations representing a linear system and 3 unknowns, and they do not intersect anywhere. And so this would be an example of no solutions. I'm going to put 0 solutions here. Okay, so this is one illustration of 0 solutions. And I'm going to put this border to separate my pictures. Okay, so another possibility when you have 3 planes is that you have a plane here. You have one plane, and then you have another plane just like that where they never intersect, one above the other. And then you have one that juts across between them. See that? Okay, so now you have another plane. The screen ends there. You see though, right? That plane keeps going up. So now you want to know how many points are in your intersection of all 3 of those planes. So first I'm going to just draw this dotted line here. This dotted line is where the bottom plane is intersecting with the jutted one. And then this top dotted line is where the jutted plane is intersecting with the top plane. Okay? So tell me, how many solutions are there? How many points are in all 3 planes? So for Zana, you're the one with I see video on. So I heard you say 4, right?
Yeah, I mean, I think so. Say 4.
So tell me where those 4 points are that you're looking at.
So the dotted lines, I think it's just, yeah, the ends of the dotted lines. Yeah.
So like here, right?
Yeah. One here, one over there. Yeah. And the same with the second line too.
And this one, right?
Yeah.
And this one. So these are the 4 points you're saying are on all 3 planes? Now what I want you to do is look at this point, right? Now I'm going to label these planes. I'm going to label this plane as P1. I'm going to label this plane as P2. And I'm going to label this plane as P3. Does that make sense? Okay, this point that I circled for you, is it on P2? It is, right?
Yeah.
Is it on P3?
No, I mean,
P3 is the jutted one. P3 is the jutted one. Is it on that one? This is P3. P3 is the one here. See that point?
that's P2, right?
No, this is P3.
Okay, yeah.
3. P1 is here. P2 is here, and P3 is this one.
No,
Let's
but
start again. Is this point on P2?
yeah, that's P2 point.
Okay, now is that point on the 3rd plane, P3?
Yeah, it is.
It is.
Right, but I want to ask for Zana. I want her to get it. See P3? This is the plane P3 right here,
Mm-hmm.
right? You see that goes through that point?
Yeah, it's the same point for P3 too.
So that point is on P3, right?
Mm-hmm.
And it's on P2, right?
Yes.
Is it on P1?
Yes.
Where's P1?
Just below P3 and above P2.
Here, right?
Yeah.
But look at where P1 is. It's above it. Is it really crossing that point, P2? It's just a single point. It's just this one point.
Mm-hmm.
You're saying what I'm going to do is I'm going to color this. That's the point there, right? I'm going to color this point, the color that I drew that plane P1, right? That's the point, right?
Mhm.
Is that point on this light blue plane? right? It's going out in all directions, right? But it's above it, right? It's
Yes.
above it. This
Yeah.
point you're labeling is on this plane here. That's below it. This is P1. You see how this point, single point here is not on this plane above it? It's on the plane P2, which is,
Oh, okay.
see that? If you were to stand on this lower plane, but you were really short, you would
Mhm.
not be touching the top plane, right? Make sense?
Yeah.
Okay, so this point here is not on P1, which means that it is not on all three planes. Once it's not on one of them, it is not on all three.
So
Right?
then how many points are there?
Okay, so you agree with me that, oh, sorry, no. You agree with me that this point is not a point on all three planes.
Mm-hmm.
That's why I made it red. Okay, and so think about the same thing here. Is this point on all three planes? Is this point on the lower plane here? This is P1. This is P1. This is P2. And this jutted plane is P3. This point is on P1 and it's on P3, but it's not in P2.
Yeah.
See that? It's not on all three planes.
Uh-huh.
This red point here, it's on the lower plane. It's not on the higher one. So this point here is not on P1. So it is also not on all three planes. And this point is on the jutted plane and it's on the top plane, but it's not on the lower plane. See that? So all four of these points are not on all three planes. And so that means that, and neither any of the other points. So there are, how many solutions are there to this linear system?
So there's like one solution.
How many points are in all three planes?
How many points? The four.
So what I'm trying to show you is that all four of these points, each of them is not on every plane, right? Right? And you didn't think any of the other points worked, so there are 0 solutions. Okay, so there are 0 solutions to this system represented by those three planes, because there are no points that lie in all three of those planes. So there's office hours every Thursday. So if you need help with this, you can come to office hours.
Yes, thank you.
Okay, so I have to keep going now. Okay, so the next graphical representation is the following. If you have, I'm going to have to draw it in stages, so I'm not going to be drawing it directly. You'll see what I mean once I draw the picture. It's a little weird. In math, weird things happen all the time. This is another one of those weird things that happen. Weird is the hardest to illustrate. This point continues here. There's the next plane. Oh, I ran out of space. Oh, it's all right. That's still the same plane from over there. Then what I want to do is continue this thing here. Then I'm going to continue this line that's going to go behind that one. Okay, so you see, kind of see how what's happening here. You have this one plane that's just vertical. You have another plane. You have a plane that's vertical. You have another plane that's kind of going through it like this. Right, so it's jutting out and this way, right? So it's kind of like a T, but like lowercase t, it's going out. But then you have one that's just at an angle that goes through the sideways part of the T, and it goes through the vertical part of the T. And it's a third plane. Okay, and so if you look at how many points are on all three of these, this is also 0. There are 0 points in all three of them. And so this corresponds with the linear system with also 0 solutions. So this has 0 solutions also. Okay, and so that's another possibility, and then we keep going because there's more. So those are three.
During exam, we don't have to draw these, right?
I mean, I could ask any test question, but just let's just go through it. So those are 3. Another possibility, they get a little easy. Some of them are easier. If you have this one, I'm gonna draw the same thing. I'm just gonna draw it better. Okay, you have this as your top plane. You have this as your bottom plane, and then your top plane. There's 2 that coincide. So you have 2 that coincide. So these are 2 planes here at the top. So 2 of the planes coincide, and then 1 plane is distinct to those 2 in parallel. So 2 of them are exact same, they coincide, and 1 is below it. 1's below it, and there's 2 that coincide above it. And so then there are 0 solutions to that system also. Okay, and so I'm thinking about this generally. So if you have a system where the bottom 2 coincide, and then there's a top one, that's the same idea. Okay, so you have 2 that coincide at the top, and there's 1 at the bottom. That's the same thing as 2 coinciding at the bottom, 1 at the top. Okay, so I don't care about where it's at the top or at the bottom. The idea is that 2 coincide, and then there's another one that's separate from those 2 that coincide. Okay, so that's another possibility. Okay, I'm going to go to the next slide now. So those all had 0 solutions. All 4 of those had 0 solutions. Now let's look at one with 1 solution, right? So it's kind of interesting to think, how could you have 3 planes that intersect only at 1 point? So I'm going to draw that now. And so this requires a little bit. This requires a little bit of work for me to draw. Being someone of terrible artistic talent, I have to draw this thing now. Okay, so now, but I'm good at drawing math things, so that's good. Okay, so then, so we have this. In real life, I'd be better at this if it wasn't on this computer screen. Okay, so then you have this, and it goes there, and then okay, it's kind of like a room where if you go to the corner of a room, let's say you have a room, an empty room, and you go to a corner of it on the floor. Think about that corner point on the floor. You have the floor, but imagine the floor going out to forever, right? And you have a wall. Imagine the wall going out in both directions, up and down forever, left, right. And you have another wall also going left, right, up and down forever. That 1 point in the very bottom corner of the room, that's the exactly 1 intersection point of those 3 planes. This point right here. So I'm going to denote that point in blue. So this 1 point is like the bottom corner of a room. the two walls and the floor intersect at that exact one point, all three of them, okay? You have a point just on one wall. You have a point just on one floor. You have a point just one other wall. You have a point on both walls, but not on the floor. You have a point on the floor that's on one of the walls. You have a point on the floor on one of the other walls. There's only one point that's on the floor and on both walls, that corner point. Okay, and so that corresponds with exactly one solution of your linear system. And this is the only way graphically you could have three planes meeting at exactly one point. Okay, if those three meet at one point, it's like a corner of a room. One solution. Everything else is plural. Zero solutions, infinitely many solutions. So, okay. So that's one solution. Now, so then everything else can be infinite. So now if you have, so now if you have this, which is a sheet going up, down, left, right in all directions, a plane, you have another plane like this is going to another plane like this that's going to the left, right, up, down, all directions. And then you have another plane like this that's slanted. It's going slanted up, down, and slanted left, right in all directions, right? So it's kind of like a book. You know, it's like a notebook or a book where if you had the two things like this, but then you had a third page in the middle that was like up, that's kind of like what's happening here, but it's not bending, right? So you have 3 pages in the book, and each page is representing a plane containing that page, right? And so you can see that red means it's a non-intersection point. Okay, so in these pictures, when I have a red, something's red. Oh, sorry, no, it is an intersection point. Blue. Okay, so the blue is illustrating where points where it's on all 3 lines, right? And I'm just going to go back for a second, right? The red was when it's not an intersection point. Okay, blue means it is. Okay, so all these points on this line is on this plane, it's on this plane, and it's on that plane. So all the points in this line are all 3 planes. And the number of points on the line, or there's infinitely many points on the line. And so this linear system has infinitely many solutions. But I'm going to write infinity symbol instead of the word infinity. Infinitely many solutions. Okay, and so now that is what happens. You have infinitely many solutions. That's one way you can have infinitely many solutions. Okay, I'm going to go to the next page. Another way you could have infinitely many solutions is if you have 3 planes that all coincide. And so if all 3 of your planes coincided with the same plane, then that would represent this would be 3 planes. Then this would have infinitely many solutions also. It would be every point on all 3 of those planes would be a solution because all 3 of those planes coincide. Okay, so that would have infinitely many solutions. And then if you have 2 planes that coincide. Okay, so if you have 2 planes that coincide, this is 2 planes. And then you have 1 plane that does not coincide, but it's its own plane. But then it let's just do it like that. Okay, so now you have two planes that coincide here, and you have one plane vertical like that. Well, you have the intersection points are all along this line. And so this also has infinitely many solutions. Every point in that line is on all three of those planes. Okay, and so now you have that also. Okay, so these are all the ways, these are all the relationships of three planes in the XY plane. Up to some obvious changes. You know, like you could have two planes that coassign vertically and one horizontal, right? So up to some minor inconsequential changes, these are all the relationships between three lines in the XY plane. Okay, so you have those two again, you have these two, and these two. So that's 2, 4, 6, 8. So there's 8 there. Okay. Okay, so if you have a linear system of 3 equations and 3 unknowns, and then you represent each of the 3 equations in that system as planes, then your 3 planes would fall into one of these 8 categories. Either it would look like one of those two, it might look like one of those two, it might look like one of those two, or it might look like one of those two. Okay. So now I'm going to go back to the whiteboard. Okay. So every system of linear equations has 0, exactly 1, or infinitely many solutions. There are no other possibilities. Okay, so as you can see from those pictures, that was for one particular case of a linear system. This is in general for any linear system. It is exactly 0, exactly 1, or infinitely many solutions. Example 2, a linear system with one solution. Okay, so let's say the example is solve the following linear system. So that linear system, let's say, is x minus y is equal to 1, and 2x plus y is equal to 6. Okay, solution. We can eliminate x from the second equation, right? By adding negative 2x to both sides of that. By adding negative adding 2 times the first equation in the system to the second equation in the system. This yields the simplified and equivalent, meaning it has the same solutions. This yields the simplified system. So first we had the first equation, x minus y is equal to 1. Then what we did was we added negative 2 times this equation to this one. How you do that is if you take this equation and you multiply it by negative 2, you take everything in it, multiply it by negative 2, and add it correspondingly here. So negative 2 times x is negative 2x. Add it to 2x and you get 0x. You have a negative y here. Multiply it by negative 2, you get positive 2y. Add positive 2y to y, and you get 3y. So then you have 3y, and then take that 3y and equals, and now the -2 on the right side, -2 times 1 is -2. Add the -2 to 6 and you get 4. So this linear system. This linear system is the result of taking the first equation, multiplying it by -2 and adding it to this one. That means the first equation stays the same. And then you're adding -2 times it to the second equation, which means the second equation changes only. So now you have this simplified system with the same solutions as the original system. So the act of adding -2 times the first equation to the second does not change the solutions of the new system, of the changed system. So even though this system consists of different equations, the solutions to this linear system is the same as the solutions to that one. Okay, and it's simple. It's a simpler system because the equation 3y equals 4 is obviously simpler than 2x plus y equals 6. Okay, and so from the second equation, we obtain easily that y is equal to 4/3. Right? So I'm not saying easily to be pretentious. I'm using the word easily to say that, right? You can see that obviously that it's much easier to find, it's easier to find y here. 3y equals 4 means y equals 4/3, right? And so that was the point of doing this algebra, to get a system in which getting the answer is easier. That's what simplified means, right? Having a simplified problem means having an easier to get solution. And so you simplify the system so that finding its solutions is easier. Okay, so from the second equation, we obtain easily that y equals 4/3. Substituting this value for y into the first equation, we obtain x is x minus 4/3 is equal to 1. Or equivalently, x is equal to 4/3 plus 1. Or equivalently, x is equal to 7/3. Okay, so after we found y equals 4/3 from the second equation of the simpler system, we plug in that solution for y into here, and then we solve for x, and we get x has to equal 7/3. So thus, the system has the unique solution x equals 7/3. Y is equal to 4/3. Okay. Right. How do we know that the original system? Because what I said before is that the act of adding -2 times the first equation to the second and getting a simplified system did not change its solutions. And so knowing that the solutions of the second system is x equals 7/3 and y equals 4/3, and the way I changed it didn't change its solutions, the solutions to this is the same as the solutions of that. So the original system also has the same solution, x equals 7/3 and y equals 4/3. Okay. Geometrically, this means that the lines represented by the equations in the system intersect at the single point 7/3, comma 4/3. We leave it to the reader, so for you, sorry, to check. I had my notes say to you. I don't know why. We leave it to you to check this by graphing the lines. Okay, so if you graphically draw this line, and you graphically draw this line, and then you see the intersection point and you find it, you'll find that it's this point. Okay, if you find it correctly. Okay, so then example 3. A linear system with no solutions. Okay, so solve the linear system. Okay, so this is going to be a linear system with no solution. So the first system is x plus y is equal to 4. And the second line is 3x plus 3y is equal to 6. Okay, so you have that linear system, and we'll find solutions. Okay, so x plus y plus 4, 3x plus 3y equals 6. Solution. Okay, so we can eliminate x from the second equation by adding -3 times the first equation to the second equation. Okay, that gives us the following linear system. Right, so you have the first equation x plus y is equal to 4, and then if you take -3 times the first equation, add the second, -3x plus x is 0x, -3y plus 3y is 0y, so the left side is 0, and then -3 times 4 is -12. -12 plus 6 is -6. As a result is this. Okay, so now from adding -3 times the first equation to the second, we get a linear system with the same solutions as the original system. Okay, so the act of multiplying one of your equations by a constant and adding that constant multiple of one equation to another does not change the solution set of your system, of your resulting system, the original. So that means the new thing you get is x plus y plus 4, which is the same, but then the second equation becomes 0 equals -6. Okay, so the question is, what are the solutions of this linear system? And so the answer I'm giving you, because it says a linear system with no solutions, so I've already told you there's no solutions, but can someone explain to me why there's no solutions? Anyone? Okay, so I'm looking at the chat. Right, so again, I want you to do it out loud because imagine me drawing these pictures. Right? How can I see the chat while I'm doing it? Okay, so there's no variable in the second equation. That's true. But what if the equation was 2 equals 2? Right? Would there still be no solutions? Right? So it's not just that there's no variables in the second equation. That's not specifically the reason why there's no solutions. Now, Harminger said 0 doesn't equal -6. 0 does not equal -6, right? And so that's the reason. But to be a little more specific, right? If your linear system has an equation that's always false, like 0 equals -6, a solution is the assignment of all the variables in your linear system. So your variables in this system are x and y. So to have a solution, you need to be assigned values to x and y to make every equation true. One of those equations is 0 equals -6. There is no assignment of the values x and y in which 0 equals -6, right? And so that means there are no solutions. That's the kind of precise explanation of why there are no solutions. There are no assignments to the variables in that linear system x and y that would make 0 equal to -6, obviously, right? And so that's the obvious reason why there are no solutions in that linear. That's an explanation of the obvious reason, which is a little complicated. Okay. Right. So this linear system has no solutions because there is no assignment of values to the unknowns in the system x and y that makes the second equation true. or there is no assignment to x and y, the unknowns in the system, that make 0 equal to -6. Okay. Okay, so that system has 0 solutions. It's not necessarily obvious when you look at the original one, x plus y equals 4 and 3x plus 3y equals 6. When you first look at that, you may think that might have a solution, one or infinitely many. But then when you simplify it correctly, now it becomes very obvious that there are no solutions. So working with simplified linear systems is much better than trying to get the answer from the original system, right? So the goal is usually going to be to simplify the system first before we find its solutions. Okay. Example 4. A linear system with infinitely many solutions. Solve the linear system 4x minus 2y is equal to 1, and 16x minus 8y is equal to 4. So you have this linear system. So the goal is find all the solutions to this linear system, solve the linear system. Solution to the problem, not this. Okay, solution to problem. Okay, so we can eliminate x from the second equation by adding -4 times the first equation to the second. Okay, so how am I getting these operations, right? Well, you have a 16x here and you have a 4x here. So if you take 4 and you multiply it by -4, you get the opposite of 16, -16, right? You want to add the thing to 16x, that would make it 0. So you want to add the opposite of 16x to get 0. And the opposite of 16x is -16x. So you want a -16x to add to 16x to get 0. So how do you get -16x from 4x? You multiply it by -4. So -4 times 4x is 16x, is -16x, and you add to that, you get 0x. And that's how you eliminate x from the second equation. Okay, so we do that and get the simplified system. We get this simplified system. So the first equation stays the same, right? So the linear equation you're using in the operation doesn't get changed. So the first one stays the same. And then you're taking -4 times that, and it's in second. The x's cancel. -16x plus 16x cancels. -4 times -2y is +8y. And then you add it to -8y and you get 0. So left side becomes 0. And then -4 times 1 is -4. -4 plus 4 is 0. So the second equation becomes 0 equals 0. Okay, so now you get the simplified system, 4x minus 2y equals 1 and 0 equals 0. Since the second equation is always true, we can ignore it. Okay, so now let's just look at 4x minus 2y is equal to 1. If we find all the solutions to 4x minus 2y equals 1, that's the same as all the solutions to linear system with that same equation, 4x minus 2y equals 1, and the additional equation 0 equals 0, right? So every assignment of values of x and y satisfies 0 equals 0. Okay, so by getting rid of this equation, we do not change its solution, the solution set of the linear system. Okay, so we ignore the second equation. Now we only look at the first one, 4x minus 2y equals 1, and we ask ourselves, what are all the solutions to this linear system? Okay, so geometrically, simplifying the original system to exactly one linear equation means that our original system can be represented as two lines that coincide. They're the same line. Okay, so now this linear system is actually geometrically two lines that are exactly the same line. Okay, and so we know that there are infinitely many solutions because that's what happens in that case. Okay, that means that the original linear system has infinitely many solutions. We can express those infinitely many solutions using using what are called parametric equations. Okay. So let me explain what I mean by parametric equation. Let y equal to t. Then that means that x is equal to, well, so then the equation so now plug in substitute t for y in the equation 4x minus 2y equals 1 and solve for x. The resulting equation is a solution for x in terms of t. Okay, so you have 4x minus 2t is equal to 1 because you let y equal to t. So if you let y equal to t, then that means 4x minus 2t equals 1. Then solve for x in terms of t. So you can divide both sides by 4, and you have x minus 2/4 t is equal to 1/4, right? Because you divide both sides by t. And so then add 2/4 t to both sides. You get x is equal to 2/4 t plus 1/4. And 2/4 is 1/2, right? So then that means that x is equal to 1/2 t plus 1/4. And so this is a representation of x in terms of t. Our original assignment of y to t means that we've already represented y as using t, and now we've represented x as only t. So here, this one line with two variables in it, if we can express both x and y using this equation in terms of only one other variable t. And so that's an example of parametric equations. Okay, so we now have parametric equations to express all the solutions of the simplified linear system 4x minus 2y equals 1. Okay, those parametric equations are, so x is equal to 1/2 t plus 1/4, and y is equal to t. Okay, each value of t that you plug in will give you a different assignment of values to both x and y, which satisfy every equation. In this case, there's only one equation. So each value t you plug in will give you a different assignment of values to both x and y, which satisfy every equation. In this case, there's only one equation of the linear system. Okay. So these are the parametric equations expressing all the solutions x comma y of that linear system. Okay, if t is equal to 0, then x comma y is equal to, well, x is equal to 1/4, and then y is equal to 0. And that's a solution, is a solution to the linear system. Okay, if t equals 1, then x comma y is equal to, well, if x is 1, then 1/2 times 1 is 1/2, 1/2 plus 1/4 is 3/4, and then y is 1. And that is another solution to the linear system. Okay, and so for each value of t, there's correspondingly an ordered pair x values of x and y in the ordered pair. You have the ordered pair of two values, which is assignment to the values x and y, which is a solution to another solution to the linear system. Okay. Okay, you can confirm these are solutions by plugging in values of x and y and seeing that every equation is satisfied. Every equation is true. Okay. Okay, so this one linear system here has infinitely many solutions, which we expressed using these parametric equations. Okay, so let me write that as a conclusion. The conclusion of all this is that the original linear system, which I'll remind you of it, which is this. Conclusion is that the original linear system has infinitely many solutions, which can be expressed by the parametric equations that by that parametric equation. Every assignment, every value of t you use corresponds with a unique solution to the original linear system. And so since there are infinitely many real numbers you could choose for t, those correspond with the infinitely many solutions x comma y of the linear system. Okay, so you can read this again in this conclusion, and that might help. Okay.
Professor, I have a question.
Sure.
So are 0 and 1 for t arbitrarily chosen?
Yeah, I could have chosen t equals 5,000, but I didn't. But to illustrate an example of a solution using 5,000 instead of 0 would be silly, right? So I chose an easy number just so that you could see it easier, right?
Yeah.
You plug in t equals 0, you get x equals 1/4 and y equals 0, right? If you plug in t equals 5,000, you get x equals 2,500 plus 1/4, which is 2,500.25, and then y equals 5,000, right?
Yeah.
So there's nothing special about t equals 0 and t equals 1 in this example. You could have chosen any t.
Okay, thank you.
You're welcome. Okay, good question. Okay, the next example is example 5. A linear system with infinitely,
Professor,
solutions.
if t equals to 1, where did you get that 3/4? Yeah.
3/4, because if you plug in t equals 1 into here, right? What do you get for x? What is x when t equals 1?
So whenever the value of t is given, we're gonna solve for like this.
What I'm saying is that each value of t you plug in, each value of t corresponds with values of x and y determined by these parametric equations.
But then y is equals to t again.
Wait, what? Y equals t, yeah. So let's say t equals 0, right?
Mhm.
the first coordinate is x when t is 0, and the second coordinate is y when t is 0. So when t is 0, what is x when t is 0?
Then it's 1/4.
Good. And when t is 0, what is y?
0.
So that's why it's 1/4 comma 0. When if t is 0.
Okay.
Makes sense? Here, x and y are functions of t. So this is kind of technically x of t comma y of t. X and y are each functions of t. And so you're plugging t equals 0 into this function of t. Now, I don't know if this makes it easier or more complicated to understand if I write that. Is that harder or easier to understand?
I think it gets harder.
Harder, right? So I was gonna not put that there because, but there's nothing wrong. There's nothing bad about doing that. I'm telling you that it's a function of t.
Like we just like put the values of t is equals to 1 in the equation, right?
Yeah.
Okay.
Yeah. Okay. And then if you change, yeah. So if you change it to t equals 1, what is x if t equals 1 here? X equals 1/2 times 1 plus 1/4, right?
Yeah.
So 1/2 plus 1/4, that's 2/4 plus 1/4, that's 3/4.
Okay.
Make sense? Okay, so if you just plug in t equals 1, you get 1/2 times 1 plus 1/4, that's 1/2 plus 1/4. That's 1/2 is 2/4, 2/4 plus 1/4 is 3. Okay, so that's how you get if t is 1, x is 3/4. And
So
then
what's our actual answer to this problem?
what?
Like what's going to be the actual answer for this problem? For this
Right, so the original problem was solve the linear system, right? So solving a linear system means finding all of its solutions, not just one, right? So so saying 1/4 comma 0, that's one solution corresponding to t equals 0. So what we want are all the infinitely many solutions. So in order to tell the reader what all infinitely many solutions are, you don't want to list infinitely many ordered pairs, right? So instead what you do is you make parametric equations. These parametric equations are telling the reader that instead of writing down the infinitely many ordered pairs that are the solutions, you're telling the reader, well, there are infinitely many real numbers that you could use for t. Each of those t values will give you x comma y, which is a solution to that linear system. Does that make sense? So you're expressing the infinitely many solutions by these two parametric equations,
Okay.
where the infinitely many values of t correspond with the infinitely many ordered pairs x comma y, which each represent its own unique solution to that linear system.
Okay, so basically the parametric equation is our answer.
Yeah, exactly. We solved the original problem because the parametric equations tell the reader what, because the parametric equations tell the reader what all the infinitely many solutions of the original linear system are. Okay, so in math, an answer to a problem doesn't just have to be the solve. Like if normally you were taught maybe that in order to give the answer, if the answer was 1, you tell the reader 1, right? If somebody asks you the answer to a problem, you tell the person the answer to the problem. That's the answer. But sometimes the answer is too complicated to tell, right? If there are infinitely many solutions to a linear system, you can't tell somebody all infinitely many solutions. So instead, mathematicians have an indirect approach to giving the answer. And so that indirect approach is by giving the person the equations which will yield all those infinitely many solutions. So those two parametric equations tell the reader what those infinitely many solutions are. So instead of giving the information, you're giving the person the information they need to get them. That makes sense? And that's the answer. The answer is the information to get those solutions. Okay. Okay, so example 5 is a linear system with infinitely many solutions. Solve the linear system. So x minus y plus 2z is equal to 5. 2x minus 2y plus 4z is equal to 10. And 3x minus 3y plus 6z is equal to 15. Okay, so you have this now, this another linear system. Okay, and you want to solve it. So you want to find all of the infinitely many solutions. Well, you want to find all the solutions to it. Okay, so if you just look at this equation, if you just inspect it, you can see that the second equation is 2 times the first equation. And the third equation is 3 times the first equation. And so by inspection, you see that the second equation is 2 times the first. And the third equation is 3 times the first. That means by simple algebraic operations on equations, you can get rid of the second and third equation from the system and simplify it to the following system. So your new simplified system is just the first equation, x minus y plus 2z is equal to 5. Okay, so you just, in a sense, see that by adding -2 times the first equation to the second, you get 0 equals 0. Adding -3 times the first equation to the third, you get 0 equals 0 again. And the equation 0 equals 0 is always true. And so by removing it, you're not affecting the solution set to the system. The solutions are the same with or without the equation 0 equals 0 in the system. And so you're left with only one equation, x minus 2y plus x minus y plus 2z equals 5. Okay, and so now the solutions to the original linear system are all the points x comma y comma z, which satisfy this one equation, x minus y plus 2z equals 5. Okay, so all the points x comma y comma z, which satisfy that one equation, are all the points x comma y comma z that satisfy all 3 of the equations in the system just above it, which means they are all the solutions of the original linear system. Okay, so what we want are all the points x, y, z that satisfy that one equation, x minus y plus 2 is equals 5. So that might seem hard, but once you understand how to make parametric equations, it's very easy. So once you understand parametric equations, this is very easy. Okay, so let's let the last variable be t. So let z equal to t. Okay. Sorry. Let y equal to s, and let y equal to s and z equal to t. Okay, so why am I now having 2 letters here where before it was only t? Because there's only one equation. There's one equation and 3 unknowns, which means that in order to use parametric equations, we need 2 variables because we only have one equation. So if I let y equal s and z equal to t, I'm going to let y equal to r and z equal to s, rs. Okay, and so then let y equal r z equals s. Then x is equal to. So then x is equal to, if you look at this equation here, x is equal to y minus 2z plus 5, because you move the y, the minus y moves to the other side, you get plus y, the plus 2z moves to the other side, you get minus 2z. But then y is r, so it's r minus 2s plus 5. And so we have x is equal to, so x is equal to r minus 2s plus 5. Okay, and so the parametric equations that represent all the solutions to the original linear system are x is equal to r minus 2s plus 5. Y is equal to r, and z is equal to s. Okay, and so those are the parametric equations representing all solutions to the original linear system. Okay, the way to interpret / understand these parametric equations is to see that for any assigned values for R and S, for each assignment of values for R and S, you have correspondingly values for X, Y, and Z, such that the order triple X comma Y comma Z is a solution to the original linear system. I'm kind of saying the same things over and over again, but it's might be a little hard to understand, and so I'm doing that. Okay, so these parametric equations are using two parameters. They're called parameters. So R and S are parameters, and so you need to choose values for each parameter. And so once you choose a value for R and S, that determines values for X, Y, and Z, such that the order triple X comma Y comma Z is the solution to the linear system. So R and S are each real numbers, and so they each have large infinities, many possibilities, right? Little r can be any real number, little s can be any real number. So for any choice for R and S, you have correspondingly an ordered pair X comma Y comma Z as a solution to the original linear system, okay? And so in that way, we represented infinitely many solutions, an even larger infinity, and even larger infinitely many solutions using parametric equations. Now we needed two parameters to express this infinity because it's even larger than the other one. They only required one parameter. Make sense? Okay, so specific solutions can be obtained by choosing values for each parameter. So if we choose R to equal 1 and S equals to 0, we get the solution. Well, if R is equal to 1 and S equals to 0, you get 1 minus 0 plus 5. You get 6, comma, then R is 1, so Y is 1, and S is 0, so Z is 0. Okay, so if we choose R equals 1, S equals 0, we get the solution 6, comma, 1, comma, 0. Okay, so we're going to stop here, and there's still no homework. Okay, and so next time we'll just keep correcting 1 point. Yeah, okay, so still no homework. So let me just check the attendance one more time before you go. Did I close the gradebook again? Yes, I did. Okay, open the gradebook. Share. Stop share. Okay, good. So now I'm just going to ask if those people are here again. Is Eldon here? Eldon Canto Marquez. Is Eldon here? Is Eldon here? Okay. Is Ahmed M. Hassan here? Ahmed M. Hassan, are you here? Is Kader Jahangir, are you here? Kader Jahangir, are you here? No, okay. Is Muhammad A. Khan, are you here? Muhammad A. Khan, are you here? Okay. Is Saqib Mahmood, are you here? Sakib Mahmood, are you here? Okay, so I still need those 5 people in the attendance. Everyone else, you've been marked present unless you just joined the class and I never marked you present and I'm not on the attendance list and I'm not aware of it. Is there anyone in the, again, same questions before, is there anyone in that circumstance? Maybe you just joined the class, I don't yet see you on the attendance list. You're here, I never marked you as present. Anyone like that? Okay, sounds good. So I'll see all of you next. I'll see all of you on Thursday. Okay. Have a good night. Thanks for being here.
Good
See
night,
you soon.
Professor. Have a good one.
Night. Thanks. You too.